In the late 1960s, the engineers at McDonnell Douglas faced a brutal geometric puzzle when mounting the third engine on their new wide-body passenger jet. Rather than burying the engine in the rear fuselage and using a curved intake duct like their primary competitor, they decided to mount the massive General Electric high-bypass turbofan dead center through the vertical stabilizer. This architectural decision required a colossal, custom-machined piece of aluminum known as the banjo forging to route the tail structure entirely around the engine core. It was an incredibly heavy, structurally complex solution that subjected the tail assembly to immense acoustic fatigue and high-frequency vibration, yet it definitively saved the engine compressor blades from intake airflow distortion during steep climbs. This single bizarre engineering choice encapsulated the entire corporate philosophy of the McDonnell Douglas DC-10. Solve an immediate aerodynamic problem through brute force engineering, even if it creates a cascading series of maintenance and logistical nightmares down the line. The origins of this unique and highly controversial trijet stem directly from a specific set of operational demands issued by American Airlines executive Frank Kolk in 1966. Kolk recognized that the upcoming four-engine Boeing 747 was simply too large and expensive for domestic transcontinental routes, so he demanded an aircraft capable of carrying 250 passengers from New York to Chicago or Dallas with wide-body comfort. Initially, he pitched a twin-engine design to the manufacturers, knowing that shedding an entire propulsion system would drastically cut maintenance costs and reduce the fuel burn per passenger. However, the commercial engine technology available at the time simply could not produce the massive thrust required to get a heavily loaded twin-engine widebody safely off a short, hot runway if one of those engines failed at rotation. Furthermore, the Federal Aviation Administration strictly regulated the oceanic and remote routes of twin-engine aircraft, legally preventing them from flying more than 60 minutes away from a suitable diversion airport. To satisfy both the raw thrust requirements for shorter runways like New York's LaGuardia and the highly restrictive routing regulations, McDonnell Douglas realized they had to compromise on a three-engine layout. This specific compromise birthed a fiercely competitive, almost ruinous race against the Lockheed L-1011 Tristar, an aircraft built to fulfill the exact same airline requirement. The resulting financial pressure on McDonnell Douglas was immense, forcing an accelerated design timeline that heavily prioritized getting their metal to market before Lockheed over-executing a flawless, unhurried development cycle. Corporate leadership at the newly merged McDonnell Douglas knew that whichever aerospace manufacturer captured the initial bulk airline orders would likely lock the other out of the medium-haul wide-body market entirely. If detailed technical breakdowns of aviation design and airline strategy interest you, subscribe. I have got more of these coming. Opting for the straight-through layout for the tail engine solved the immediate issue of turbulent airflow entering the compressor blades, a phenomenon that historically plagued S-duct designs during high angles of attack. By keeping the intake duct perfectly straight, the General Electric CF6 turbofan could operate at absolute peak thermodynamic efficiency, translating directly to lower fuel burn during the demanding climb out of high-altitude airports like Denver. However, elevating a massive engine weighing over 8,000 pounds nearly 30 feet above the fuselage created severe structural headaches for the airframe design team. The vertical stabilizer had to be reinforced to an extreme degree to prevent devastating aerodynamic flutter, adding thousands of pounds of dead weight to the extreme rear of the aircraft. This extra structural weight shifted the aircraft's center of gravity drastically rearward, which then forced the aerodynamicists to shift the entire main wing further back on the fuselage just to maintain basic flight stability. Shifting the swept wing rearward created a secondary aerodynamic penalty by altering how the aircraft pitched during critical low-speed approach maneuvers. To maintain sufficient pitch authority during the flare and landing phase, the horizontal stabilizers had to be significantly upsized, increasing both manufacturing costs and parasitic drag in long-haul cruising flight. Yet airline executives initially loved the elevated tail engine position because it placed the power plant completely outside the main fuselage pressure vessel, making engine swaps theoretically much faster than on the competing Lockheed widebody. Mechanics could drop the entire tail engine straight down onto a specialized cradle without dismantling heavy structural bulkheads or breaching the cabin pressure seal. This promised ease of maintenance was a massive selling point in airline boardrooms, where time spent on the ground equaled thousands of dollars in lost revenue. But the reality on the ramp was entirely different. Ground crews quickly realized that the engine was positioned so high off the tarmac that specialized, highly expensive custom-built cherry-picker cranes were required just to routinely check the oil or inspect the fan blades. Beyond the towering mechanical challenges of the tail engine, the McDonnell Douglas engineers were utterly obsessed with maximizing the revenue potential of the lower cargo deck. In a traditional narrow-body jet like the Boeing 707, luggage was hand-loaded into small, irregularly shaped bins. But the new wide-body era introduced massive standardized cargo pallets. To easily accommodate these lucrative freight pallets alongside standard passenger baggage, the McDonnell Douglas DC-10 required enormous cargo doors cut into the lower fuselage structure. To maximize the usable interior volume and prevent the door from eating into cargo space, engineers designed these huge doors to open outward, rather than plugging inward like traditional aircraft passenger doors. An inward opening plug door uses the immense pressure of the passenger cabin to physically wedge itself tighter against the airframe as altitude increases, making it an inherently fail-safe piece of engineering. By stark contrast, an outward opening door relies entirely on a complex, highly stressed series of mechanical latches and locking pins to hold back tens of thousands of pounds of pressurization force. To reliably secure this outward opening structural door, the design team utilized a motorized latching system driven by small electric actuators. But here, the relentless drive to save airframe weight and simplify the manufacturing process introduced a terrifying vulnerability into the foundational aircraft systems. Instead of employing a robust, heavy-duty hydraulic locking mechanism, the electric motors drove a series of over-center cams that were supposed to physically lock the steel pins into place around the door frame. If the electric motor did not fully rotate the cams to the correct geometric angle, the door could easily appear closed to the ground crew outside and the flight deck crew inside, but remain structurally unlatched. The engineers attempted to solve this glaring issue with a small external viewing window and a secondary mechanical lock pin, but the internal physical linkage was far too flimsy. The linkage could be easily bent and forced into the supposedly locked position by a strong baggage handler pulling on the exterior handle, even if the primary heavy-duty latches were not fully engaged. This specific mechanical weakness meant the aircraft could frequently take off with a literal ticking time bomb sitting in its belly, waiting for the pressure differential to build. When a massive lower cargo door violently blows out at 20,000 feet, the densely pressurized air in the passenger cabin above immediately rushes down into the cargo hold to equalize the internal pressure. In the McDonnell Douglas DC-10, the floor beams separating the upper passenger cabin from the lower cargo hold were simply not designed to withstand this sudden, violent aerodynamic pressure differential. The cabin floor would catastrophically cave in, which was a fatal design oversight because the routing engineers had decided to run all the primary and backup flight control cables directly through those exact floor beams. Therefore, an explosive decompression in the lower cargo hold would physically snap the control cables and sever the hydraulic lines running to the tail section, instantly stripping the pilots of their mechanical ability to control the elevator and the rudder. The corporate pursuit of maximum cargo revenue had inadvertently, yet directly, linked an exterior baggage door latch to the ultimate survivability of the entire flight control system. When the first major incident regarding this floor collapse occurred over Windsor, Ontario, the skilled flight crew miraculously managed to land the severely crippled jet using only differential engine thrust. Instead of immediately grounding the global fleet and forcing a heavy, expensive mechanical redesign of the latching mechanism, the manufacturer and the Federal Aviation Administration entered into a highly controversial gentleman's agreement. McDonnell Douglas promised to issue service bulletins advising airlines to voluntarily install a simple support plate to prevent the lock tube from bending, avoiding the terrible public relations disaster of a mandatory airworthiness directive. This weak regulatory response proved to be a catastrophic failure of oversight, as the complex paperwork and optional nature of the fix meant that several airframes slipped through the maintenance cracks entirely unmodified. This boardroom failure directly culminated in a tragic accident outside Paris 2 years later, where an unmodified door blew out, the floor collapsed, the control cable snapped, and the pilots were left entirely powerless to stop the aircraft from diving into the forest. Despite the severe vulnerabilities hidden beneath the passenger floorboards, line pilots who transitioned to the new trijet from older, heavier-handling first-generation jetliners often highly praised its flight deck and handling characteristics. The McDonnell Douglas DC-10 featured a relatively modern, exceptionally spacious cockpit with enormous windshields that provided excellent forward and downward visibility during complex visual approach procedures. It utilized an advanced analog autopilot system theoretically capable of executing Category 3 automatic landings in near-zero visibility, a crucial commercial feature for airlines heavily operating out of fog-prone superhubs like London Heathrow or San Francisco. The primary flight controls were fully powered by 3 highly pressurized, independent hydraulic systems, a mechanical setup that was standard for the wide-body era, and theoretically provided incredibly robust operational redundancy. In normal daily operations, the heavy aircraft felt remarkably stable and highly responsive to control inputs for a machine weighing well over 400,000 pounds at maximum takeoff weight. However, the nested engineering loop struck again, because the ultimate problem was not the sheer number of hydraulic systems, but rather the highly concentrated geographic routing of those vital fluid lines throughout the metal airframe. In their effort to simplify the manufacturing process and reduce the total required length of heavy stainless steel hydraulic tubing, the design team routed the lines for all 3 independent systems closely together in the extreme tail section, and again along the leading edge of the main wing. They fundamentally assumed that the uncontained explosive failure of an engine, where rotating titanium metal blades completely break through the protective Kevlar casing, was statistically improbable enough that it did not warrant physically isolating the hydraulic lines far away from one another. This geographical convergence meant that a single catastrophic kinetic event, like an exploding turbine disk or a collapsing structure, could easily slice through all 3 independent hydraulic systems simultaneously. It was a classic aerospace engineering trap, where theoretical mathematical redundancy, drawn on a pristine schematic diagram, utterly failed to account for real-world, chaotic kinetic damage. This vulnerability was ruthlessly exposed by the daily operational reality of commercial airlines aggressively trying to minimize their expensive maintenance downtime. To shave hours off a standard engine replacement procedure, airline maintenance managers devised a shortcut where they would use a massive heavy-duty forklift to remove the underwing engine and its attaching pylon as one single, incredibly heavy unit. The official maintenance manual specifically required separating the engine from the pylon first, but doing it together saved a highly lucrative shift of labor for the mechanics. The extreme precision required to align a massive forklift carrying 5 tons of metal was nearly impossible to achieve flawlessly every single time, and occasionally, the forklift operator would accidentally bump the heavy assembly against the delicate wing attachment points. This improper lifting procedure subtly cracked the aft structural bulkhead of the pylon, a microscopic fracture that remained completely invisible to routine visual inspections on the crowded ramp. When that fatigued pylon bulkhead inevitably failed during the immense physical stress of a takeoff roll, the entire engine and pylon ripped cleanly away from the wing, pivoting upward and over the leading edge. As the massive engine tore away, it perfectly sliced through the hydraulic lines routed tightly together along the leading edge of the wing, instantly draining the fluid that held the crucial leading edge slats in their extended position. Without hydraulic pressure locking them in place, aerodynamic forces immediately slammed the slats shut on the left wing, drastically destroying the lift on that side of the aircraft, while the right wing continued flying normally. The pilots, utterly unaware of the structural damage behind them and following standard engine failure procedures, pitched the nose up to climb, which inadvertently slowed the aircraft down directly into a lethal asymmetrical stall. The aircraft rolled uncontrollably and crashed, permanently searing a horrific image into the public consciousness and highlighting how a seemingly brilliant maintenance shortcut could interact catastrophically with a concentrated system routing design. The brutal economics of the 1970s dictated that daily availability and predictable mechanical dispatch reliability often trumped aerodynamic perfection and advanced avionics. Airline executives cared far more about keeping their expensive capital assets reliably in the air than they did about the aerodynamic elegance of an S-duct or the sophisticated computerization of an active flying tail. Knowing what you now know about its devastating operating costs, structural compromises, and catastrophic system vulnerabilities, do you think the brute force design approach was worth it for the airlines? Share your thoughts below. Despite the incredibly rough edges and high-profile tragedies, the aircraft undeniably fulfilled its core corporate mandate, moving extremely heavy passenger loads across oceans and vast continents at a significantly lower seat-mile cost than the early, heavy four-engine Boeing 747 variants. When the aircraft first entered rigorous commercial service in 1971, airline route planners and operations managers quickly realized that the glossy marketing brochures had aggressively masked several harsh realities of daily line flying. The initial production variant, the McDonnell Douglas DC-10-10, was strictly a domestic machine heavily optimized for standard transcontinental flights. But the massive 1973 global oil crisis utterly destroyed the foundational economic assumptions it was built upon. As aviation fuel prices rapidly quadrupled, the critical break-even load factor, the specific percentage of passenger seats an airline had to sell just to cover the operational cost of the flight, skyrocketed to unsustainable levels. Airlines suddenly found themselves flying massive, heavily depreciating, half-empty wide-bodies on domestic routes that simply no longer had the passenger demand to financially justify burning fuel in a three-engine jet. The desperate, immediate need for significantly better fuel economy and international route flexibility forced McDonnell Douglas to rapidly develop the heavier, longer-range McDonnell Douglas DC-10-30. This highly successful extended-range variant required a massive structural increase in maximum takeoff weight to accommodate thousands of gallons of additional heavy jet fuel in the wings and center tanks. To adequately support this immense additional weight without physically cracking the runway tarmac or collapsing the taxiways at older municipal airports, engineers had to add a completely new two-wheel center landing gear strut directly under the middle of the fuselage. While this heavy addition successfully solved the pavement loading problem, it created a massive logistical nightmare for ground handling crews attempting to service the aircraft during incredibly tight 45-minute turnaround windows. The additional center gear strut completely blocked easy access to several critical lower servicing panels, forcing baggage tractors, catering trucks, and heavy fuel tankers into a delicate, highly choreographed, and dangerous dance around the crowded belly of the plane. A single distracted driver or a slightly misaligned cargo loader could easily strike the center gear door, instantly grounding an aircraft that was supposed to be generating vital revenue high in the air. In direct operational comparison to its eternal corporate rival, the Lockheed L-1011 Tristar, the McDonnell Douglas product often felt decidedly less refined and much harsher to both mechanics and observant passengers. Lockheed had proudly chosen to incorporate a highly advanced, technologically complex fly-by-wire augmentation system that fundamentally made the Tristar an absolute marvel of modern aerospace engineering. However, Lockheed's total reliance on the technologically ambitious but severely delayed Rolls-Royce RB-211 engine nearly bankrupted the entire company and disastrously delayed their new aircraft's entry into commercial service. McDonnell Douglas capitalized ruthlessly on this engine delay, using their structurally simpler, slightly less aerodynamically efficient systems and highly reliable General Electric engines to rapidly capture crucial early orders from major legacy carriers. Airlines were entirely willing to accept the less elegant engineering of the McDonnell Douglas trijet simply because it was physically available to fly and generate cash, while the Lockheed alternative was still hopelessly stuck in development hell. From the specific perspective of the paying customer, stepping into the massive cabin of the McDonnell Douglas DC-10 in the early 1970s was an absolute revelation compared to the cramped, noisy aluminum tubes of the previous decade. The twin-aisle widebody configuration radically changed airport boarding logistics, allowing significantly faster passenger flow and drastically reducing the dreaded boarding bottleneck at the forward cabin door. Early promotional marketing campaigns heavily touted the expansive, high-ceilinged cabin, often outfitting it with extravagant luxury lounges, stand-up bars, and wide seating that feels like an absolute fantasy by today's brutal high-density airline standards. Some airlines even opted for a unique lower-deck galley configuration, where the entire kitchen was situated down in the cargo hold, completely removing the noisy food preparation area from the main passenger cabin. Flight attendants would load heavy catering carts into a pair of small electric elevators built directly into the cabin floor, riding up and down between the decks during the meal service. While this lower deck galley was a brilliant utilization of dead space that allowed airlines to cram even more revenue-generating passenger seats onto the main deck, it was a mechanical nightmare to maintain in daily operation. The heavy elevator shafts required massive structural cutouts in the vital floor beams, further complicating the airframe integrity, and the elevator motors themselves were incredibly prone to frustrating mechanical breakdowns. If an elevator jammed mid-flight, the flight attendants were physically locked out of the remaining food and beverage carts, completely ruining the carefully planned passenger service on a long international flight. Furthermore, passengers sitting in the very back of the aircraft experience a distinctly different and much harsher flight than those relaxing in the forward first-class cabin. The intense acoustic resonance from the straight-through tail engine, violently vibrating against the massive banjo, forging translated into a persistent, deeply fatiguing low-frequency drone that easily penetrated the rear pressure bulkhead on long oceanic segments. As the airframes aged heavily through the 1980s and deep into the 90s, the general passenger experience steadily degraded as profit-starved airlines ripped out the luxurious lounges to aggressively cram in more revenue-generating economy seats. Crucially, the rise of extended-range twin-engine operational performance standards, commonly known in the industry as ETOPS, eventually allowed highly reliable, highly efficient twin-engine jets like the Boeing 767 to legally fly the exact same remote oceanic routes as the heavy trijets. Suddenly, that third engine mounted high up in the tail transformed overnight from a strict regulatory necessity into a massive economic liability that burned excess jet fuel and required extremely expensive, heavy maintenance overhauls. Major global passenger airlines quickly began dumping their aging trijet fleets onto the saturated secondary market, where they were eagerly snatched up for pennies on the dollar by rapidly expanding global freight integrators like Federal Express. The exact same voluminous lower cargo hold that caused so many structural design headaches early on made the durable airframe a remarkably capable, highly profitable dedicated freighter. In a desperate corporate bid to keep the lucrative widebody production line alive in Long Beach and aggressively compete with the highly efficient new generation of twin-engine widebodies, the manufacturer eventually launched a heavily modernized derivative known as the McDonnell Douglas MD-11. To achieve this, they significantly stretched the main fuselage, added highly distinctive winglets to the wingtips to dramatically reduce drag, and installed a highly advanced glass cockpit that entirely eliminated the heavy cost of the flight engineer position. To aggressively squeeze out every last possible drop of fuel efficiency and compete with Airbus, aerodynamic engineers drastically reduced the physical size of the horizontal tail, which intentionally made the massive aircraft slightly less stable in cruising flight to greatly reduce aerodynamic drag. This controversial design choice, known as relaxed static stability, relied entirely on computerized flight augmentation systems to constantly keep the nose pointed safely in the right direction. But it unfortunately resulted in an incredibly unforgiving aircraft during the landing phase. Pilots flying the new derivative had to meticulously manage their precise approach speeds, because a slightly heavy landing in an MD-11 could cause the incredibly stiff main landing gear to violently rebound off the runway. This aggressive rebound would dangerously pitch the nose sharply upward, destabilizing the heavy aircraft and frequently leading to severe, catastrophic structural breakups if the pilot attempted to force the plane back down onto the tarmac. Ultimately, the heavy derivative could not successfully overcome the fundamental, inescapable economic truth of modern commercial aviation. Two engines will absolutely always be significantly cheaper to operate and maintain than three. The long twilight of the McDonnell Douglas Trijet family was a slow, smoky fade out as hard-working, soot-stained nocturnal freighters, rather than a glorious, celebrated retirement from mainline passenger service. Yet, aggressively analyzing this unique aircraft solely through the narrow lens of its early, highly tragic mechanical accidents, or its ultimate aerodynamic obsolescence, completely ignores its massive, undeniable contribution to modern global aviation infrastructure. It was the heavy, blunt instrument that physically forced legacy airlines to figure out highly complex, high-density hub operations, proving definitively that wide-body economics could work brilliantly on standard domestic routes, not just glamorous intercontinental prestige flights. It heavily democratized commercial air travel by flooding the global market with cheap, accessible seats, allowing aggressive charter airlines to offer incredibly affordable package holidays to millions of working-class people who had never previously stepped onto an airplane. The complex engineering story of the McDonnell Douglas DC-10 is an absolute masterclass in the ruthless structural compromises and intense financial pressures required by the commercial aviation industry. It perfectly highlights how a single arbitrary regulatory constraint, like the archaic 60-minute rule, can entirely dictate the physical shape of an aircraft, and how the desperate drive for corporate survival can rush deeply flawed, highly vulnerable systems into the sky. It was undeniably never the most elegant machine parked on the ramp, nor was it the most technologically advanced aircraft of its competitive era, but it was a relentless, heavily utilized workhorse that aggressively hauled the airline industry kicking and screaming into the modern era of mass transit. If you found this analysis useful, aid like helps more people discover these deep dives. Thanks for watching.